If someone were to weigh you up on the planet Uranus, would you weigh the same no matter where you stood? You might think that's a silly question. Of course you would. Gravity is pretty evenly distributed on Earth, give or take a few factors like altitude and how far you are from the center of the planet. But on Uranus, things might not be so straightforward. Scientists have found evidence that Uranus's gravity field is lopsided. But why? And what does it mean for anyone unfortunate enough to fall into its colossal depths? Welcome to my channel. If you want to understand what's going on here, we need to talk about something called the equipotential surface. This is basically the surface that a test particle would trace out if it were free to move around under the influence of gravity alone. So we can think of this surface as sort of a map of the gravitational field. On Earth, the equipotential surface is pretty close to being a sphere. The North Pole and the South Pole are the lowest points, and the equator is the highest point. That's because Earth is actually a bit wider at the equator than it is at the poles, which means you're closer to the center of the planet at the poles than the equator. Being closer to the center means you're experiencing more gravity, so you'll weigh more. So if you were to plot Earth's gravitational potential energy, which is just another way of saying weight, you'd end up with a surface that looks a lot like our planet. But when scientists mapped Uranus's gravitational potential energy, they found that the equipotential surface wasn't a sphere at all. It was tilted on its side. And by comparing the two, they were able to calculate that Uranus's gravity was stronger on one side than the other. They also found that Uranus has an unusual bulge around its equator. So even though these two factors seem to cancel each other out on Earth, on Uranus, they don't. The result is that you'd weigh slightly more at the poles than the equator, just like on Earth. But Uranus's gravity is lopsided, meaning you'd weigh different amounts depending on which pole you were standing on. Now, scientists aren't exactly sure what's causing Uranus's lopsided gravity field, and that's part of what makes this such an exciting discovery. There are a number of possible explanations, and each one suggests something different about the interior structure of the planet. But first, let's talk about why we didn't notice this before. For most planets in the solar system, the equipotential surface is so close to being spherical that we can't really tell the difference. But Uranus and Neptune are ice giants, which means they have significantly lower densities than the rocky planets. As a result, their gravity fields are much more sensitive to the details of their internal structure. Uranus's density is low enough that we can actually measure the deviations from a perfectly spherical shape. The previous measurement of Uranus's gravity was made in 1977 by the Voyager 2 spacecraft. At the time, scientists thought the gravity field was spherical, but new measurements from NASA's more precise and modern gravity probe (B) satellite show that it isn't. The measurements were taken between 2004 and 2016, while Uranus was in a specific orientation relative to the Sun. According to the model that scientists had been using, Uranus should have appeared perfectly spherical. But when they compared the observed data to the predictions, they found that there was a mismatch. There are two main factors that can cause this kind of distortion. One is an equatorial bulge, and the other is an off-center core. Now, an equatorial bulge happens when a planet rotates, and the centrifugal force at the equator pulls the planet outward, stretching it along the rotational axis. Think of spinning a bucket of water. The water forms a bulge at the equator because the centrifugal force is pushing it outward. Scientists knew that Uranus had an equatorial bulge from the 1970s measurements, and they took that into account when they analyzed the new data. But even after accounting for the bulge, there was still a mismatch between the observations and the model. So that means there must be another factor at play, something like an off-center core. To explain what I mean, let us imagine that Uranus's core is a giant ball bearing right in the center of the planet. As the planet rotates, the centrifugal force would push this ball bearing outward, just like it pushes the water in the bucket of water. But if the ball bearing were to move off center, say toward one of the poles, it would cause the entire planet to tilt. In addition, it would also cause the gravity field to be stronger on one side and weaker on the other, exactly like the observations suggest. So an off-center core could explain both the gravity and the equatorial bulge. But it doesn't necessarily mean that the core is actually off-center. It could just mean that the mass distribution inside the planet is off-center. For example, if there's some sort of dense blob lurking deep inside Uranus, that could have the same effect as an off-center core. Either way, though, this suggests that Uranus's interior is more complicated than we thought. The most likely culprit is something called convection. This is the same process that causes the currents in the ocean. Hot fluid rises and cooler fluid sinks, and over time, that sets up a cycle of motion. Something similar is happening inside Uranus. The swings in Uranus's atmosphere from extreme cold to extreme heat may be creating convection currents within the planet. These currents are carrying heat from the interior to the exterior. And that's what's powering the shifts in Uranus's gravity and its equatorial bulge. Another possibility is that convection currents are mixing different materials inside Uranus, and that's what's causing the lopsidedness. In fact, scientists have run computer models of Uranus with all of these factors in mind. And they found that they were able to reproduce the observations with a model that had an off-center core. But this isn't the only possible explanation. They can get the same result with a model that just has convection currents churning through a homogeneous interior. And to make things even more complicated, Uranus isn't the only gas giant with an off-center core. Scientists have found evidence that Neptune has one too. But for some reason, Saturn doesn't, and we still don't know why. Unfortunately, we're unlikely to get clear answers anytime soon. Uranus and Neptune are very far away from Earth, and it would take decades to get there with current technology. So for now, scientists will just have to keep observing them from afar and running computer models until we can get more data. It turns out that even though Uranus might not be the most hospitable place for humans, it's surprisingly hospitable for science. Who knows what other secrets it's hiding? Maybe there's life on Venus. Maybe Jupiter has a super powerful magnetic field. Or maybe, just maybe, we'll find another Earth-like planet that's habitable. And the only way to find out is to keep exploring. Thank you for watching this video. If you liked it, you can leave a like and subscribe if you want to see more videos like this. All the references used are added in the description below. Until next time.